Hello, everyone, and welcome back to yet another day of online learning. Today, we are going to be pushing past momentum, and we are going to be talking about our fifth and final unit for the year, which is energy. Specifically, today, we are going to be talking about kinetic and potential energy. So be sure you've gone to Google Classroom and have the notes available, as there will be points for you to stop, fill in, and make this lecture as interactive as possible, as usual. So without further ado, let's get started in talking about energy. Well, what is energy? Well, I have this kind of everyday use of the word, where a student might say, "It's been such a long day, and I don't have the energy to do my physics assignment." What they're really saying is that they can't put in the work to do their physics assignment, right? They don't have the energy, they can't do the work. So what is energy in a physical sense? Well, energy is the capacity to do work. Work is defined as a force acting over a distance, but we'll talk more about what work is in the next lecture. But for right now, energy is the capacity to do work. The more energy you have, the more work you can do. The less energy you have, the less work you can do. So there are different types of energy. There is mechanical energy, which we'll be talking about today, and the focus of most of our talk about energy, which is, kinetic energy and potential energy. The energy is due to the object's motion or an object's position. There is also, as we mentioned in the last lecture, heat energy. Well, what is heat energy? It is measured by the motion of particles. So, how fast they're moving, how fast they're rotating or vibrating. So again, it's due to the motion of the particles. There's also chemical energy, the energy stored in chemical bonds. Well, what is a chemical bond? It is the relative position of the electrons of two atoms. So again, it has to do with the position of these particles. And similarly, nuclear energy is the energy that's stored in the bonds between protons and neutrons. And again, it's due to their positions relative to one another. So energy is really defined by an object's motion and or its position relative to something else. So the first type of energy that you've already seen before is kinetic energy. So I have here the famous story of the tortoise and the hare. And we ask, which animal has a greater kinetic energy? Well, in order to answer that question, we have to define what kinetic energy is. Well, it is the energy due to an object's motion. And as you saw, the formula for kinetic energy is 1/2 mv squared, where m is the mass and v is the velocity. So which animal has a greater kinetic energy? Well, we don't know the mass of the objects, but assuming that they're the same mass, they have relatively similar masses in this picture, I would guess. We can say that the hare has greater kinetic energy because we know that the hare moves faster in the story. So here the hare has greater kinetic energy, assuming that their masses are the same. Energy is also a scalar quantity. Energy does not have a direction. It does not make sense to say my kinetic energy going west or my kinetic energy going north, because it is just a number. And it is important to note that there is no such thing as negative kinetic energy. Well, why is that the case? Well, kinetic energy is equal to 1/2 mv squared. Well, we can't have negative mass, right? That doesn't make physical sense. There always has to be at least some kind of mass, positive mass. And if you defined the right as positive and the left as negative, and you have an object moving to the left, so it has a negative velocity, that v squared, is going to cancel out that negative sign. So even if you've defined something in terms of your coordinate system, you will still end up with a kinetic energy that is greater than 0. So kinetic energy is either 0 or greater than 0. Well, what about potential energy? Potential energy is the energy that an object stores as a result of its position. And we're going to be talking about two different types of potential energy today. There are gravitational potential energy and elastic potential energy. Well, gravitational potential energy is the energy stored in an object as a result of its height. So what does that mean? It's the result of the work that we have to do to bring an object to different positions. So let's imagine we have a staircase, and we have this yellow ball and we have this purple ball. It took more work on my part to move the ball to the higher position. It took more work to move the purple ball than it did the yellow ball because it's higher. And if we remove the staircase, if it just suddenly disappeared, those balls would fall to the ground. And we would be able to get that potential energy back. So the potential energy, the gravitational potential energy is dependent on the mass of the ball or of the object and the height to which it's raised. So we have the potential energy of gravity is equal to the mass of the object times g, which on Earth is 10 meters per second squared, and the height to which it is raised. So I have this thought experiment. Let's imagine that we're back at School Without Walls. And let's walk into the front door and what is your relative potential energy in the main office? So you walk in the front door, what is your potential energy, do you think? Well, if you walk in and you're on the ground floor, you might not have any potential energy, right? We can call that the zero height point. And what about if you go up to the third or fourth floor and go to the library? Well, then you would have a larger potential energy than when you were on the main floor. But we can also go down to the physics classroom, right? So what is your relative potential energy in the physics classroom? Well, that would then be a negative potential energy from our main office. So my point here is that potential energy is a matter of reference. What does that mean? Well, where you define your zero height depends on the observer, depends on where you are. So somebody in the physics classroom might set that as their zero height. Somebody at the main office might set that as their zero height. Somebody at the library might set that as their zero height. It doesn't matter where we call our zero height. What matters is how much we change our position relative to where we started. So what we care about when we're going to be dealing with conservation of energy in a few lectures. And when we're doing these problems, we don't necessarily care where the zero height is, but we care the change in position that we undergo. So if our physics classroom, is the zero height point, and we go up to the main office, that's the same change in position as if we started at the main office and went down to the physics classroom, right? So we also have elastic potential energy, which is, and I have this picture here of this person bungee jumping, and I have this person who has stretched out a rubber band. And the question is, which object has a greater potential energy? Well, in order to answer this question, we have to define what elastic potential energy is. Well, it is the energy stored in elastic materials as a result of their stretching or compressing. So as a result of the position that we then put them in. Remember, potential energy is the energy as a result of their position. And elastic potential energy can be stored in things like rubber bands, and bungee cords, and trampolines, and springs, an arrow drawn back into a bow, things that stretch or compress. And it is given by the formula 1/2 kx squared. So remember that k is the thing that we call the spring constant, which is the inherent makeup of the spring that we are dealing with, and how much it resists being stretched or compressed. And x is the amount that we have either stretched or compressed our spring. So if we go back to our pictures on the right or on the left here, we can assume that the bungee jumper is going to, or the bungee cord is going to have a greater elastic potential energy. Why? Because it has to support the entire weight of that person. And we can assume that it's going to have a higher spring constant because of that. It also, the stretch of the spring, or of the bungee cord, is going to be a few meters maybe, whereas the stretch of our rubber band might be a few centimeters. So there is a greater potential energy stored in the bungee cord than in the rubber band. So now that we've talked about it, let's do some problems. So it says, determine the kinetic energy of a 625 kilogram roller coaster car that is moving at a speed of 18 meters per second. So take some time, do out this problem, and we'll do it back when you get, and we'll do it out when you get back. So let's see how we do this problem. Well, in order to solve for the kinetic energy, we have to use our kinetic energy formula, which is equal to 1/2 mv squared. And we were given that the mass of our roller coaster is 625 kilograms, and our speed at which it's moving is 18 meters per second, and then we have to square that. So if we do out our math, we get 100,001, 250. And what about the units? Well, we have kilograms here, times meters squared divided by seconds squared. Where did those squares come from? Well, we squared 18, so we also have to square our units. So kilograms meters squared per second squared is equal to a joule. And that is the unit that we use for energy. Now, some of you guys might notice that a kilogram per times meter divided by second squared is a Newton, because that is mass times acceleration, the units of mass times acceleration. That's a unit, Newton. So a joule is also equal to a Newton times a meter. But the standard unit that we use for energy is joules, and that is denoted by a J. So our final answer of the kinetic energy is 101,250 joules. So let's do a second example. So calculate the gravitational potential energy of a 5 kilogram mass at a height of 4 meters above the ground. And what did you choose as your zero height position? So let's see how we would do this problem. Well, the potential energy due to gravity is equal to the mass times little g times the height. So we were given that the mass is 5 kilograms. We know that g is 10 meters per second squared, and we raised it to a height of 4 meters above the ground. So similarly, we get an answer of 200 kilograms meters squared divided by seconds squared, which we just called a joule. So our final answer is 200 joules. And let's do one final example. If the elastic potential energy stored in a bungee cord is 10 joules, and it is stretched a total of 0.75 meters, what is the spring constant? So here we have the potential energy of a spring is going to equal 1/2 kx squared. Well, we were given that the potential energy is 10 joules times 1/2 k times x is 0.75 meters squared. So if we multiply both sides by 2 to get rid of that 1/2 and divide by 0.75 squared, we get 20 joules divided by 0.75 squared meters squared is going to be equal to k. And our final answer is 35.5 newtons per meter. So this is how we would do problems relating to either potential energy or kinetic energy. And it's just, just the calculations using the equations that are given to us. So in summary, we have two different types of energies that we are going to be focusing on in this class. We have kinetic energy, which is the energy of an object's motion, and that's given by 1/2 mv squared. And we have potential energy, which is the energy of an object's position. We have gravitational potential energy and elastic potential energy. So, as always, you guys have an assignment that goes along with this lecture, and that's going to be due next Thursday, May 7th at 2 p.m. And the next lecture is going to be posted up that same day on work. You see up in the corner that my office hours have changed. I'm only going to be available 2 hours from 12 to 2 from now on, Monday through Friday. But please reach out to me if those times don't work for you, and we can try to set something up. So as always, guys, thanks for tuning in, and stay healthy, stay safe, and I will talk to you all next time.